Hope everything's going well. I'm just double checking everything, making sure everything is good to go, making sure my mic works, making sure just everything's working. Hope everything's going well. It is Wednesday, August 24th, I believe, and we are going to solve a bunch of limits graphically. Now today it was just going to be reviewing the limits, but of course, if you have any questions, feel free to message them to me at theveganmathguy.com. Okay, just making sure everything's good. I'm going to go ahead and just make sure. I'm going to make sure I am sending the link. I'm letting everyone know that we are now live. This will take around 2 minutes, so you could obviously skip to where we're going to start. Get your pen and paper ready. We're doing the limits. Okay, well, okay. Again, just making sure everything's good to go. All right. So just moving everything around. So today we're going to cover limits, and we're going to cover limits just graphically. We're not going to actually solve them algebraically. It's just going to be based off graphs. So we're checking when limits are coming from the left and coming from the right. And we're going to check whether or not limits are going to exist. So if you're ready, let's get started. Okay. Let's see. Hopefully this works. Let's go ahead and do that. All right. By the way, I changed screens today as I'm going live on TikTok as well. So I'm just making sure everything's adjusted properly. So let's just talk about limits when they are being solved graphically. The whole point here is we're trying to just analyze where the function is approaching. What is the y value that the function is approaching as it's coming from the left or it's coming from the right? Okay, and it's not supposed to be as complicated as, or I'd say it's a little different than asking like, what is the y value when x is equal to something? So this is different from just asking, what is f of 3, for example? That we can just look at the graph and see what the y value is at that point, and we are good to go. But approaching something is what we use when we are studying limits. So let's just briefly talk about something like question number 1. Let me just go ahead and highlight this. Okay, if you'll notice that they're asking, what is the limit as x approaches -3 from the left side? So let's go ahead and take a look at our graph. So x is equal to -3 is right there. And again, typically, if we were asking what is f of -3, in this case, we will say that it's undefined. But we're asking what is it approaching as we're coming from the left. So just imagine you're on the left side of the graph and you're approaching the function. Again, you're coming from the left and you're trying to see what the y value is that it is that you're approaching. Now, the answer is not necessarily 1, but we're getting really, really close to 1. Again, it's not 1 because it's not defined at 1, but we're getting really, 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 really close to 1. So one can say that our answer is technically 0.9999999 and on going onward. Again, because we're approaching it, we're getting really, really close to it. But, you know, just to be for the sake of math and solving these problems graphically, we're just going to say that the answer is going to be 1. Again, it's approaching 1. So we can say that that's what the limit is. That's not the actual value, but that's what it's approaching. That's going to be 1 for problem 1. Okay, so now let's go ahead and talk about problem 2. I'll write it here on the bottom. The limit as x approaches -3. From the right side. So again, let's go ahead and observe that on our graph. We are going to -3, and as you can see on the graph, the function is at -3. We're trying to see what the y value is. Again, we are approaching it from the left side. So we're trying to see what happens, or I said from the left side, it's actually from the right side. But what happens as our function approaches 3 from the right side? What do we say? It's about 1 again. Again, it's not necessarily that it's 1, but it's approaching 1. Okay, that's not the actual value at -3, but it's just approaching it. All right, so keep in mind that the x is approaching -3 from the left is 1, and as the function is approaching -3 from the right, the function is 1. I wrote this now because we're gonna go ahead and talk about what problem number 3 is. What is the actual limit? Now, the former definition for this, or the actual definition, is that the limit is going to be the value that it approaches from the left and from the right at the same time. So if the function is approaching the same value from the left and from the right, then the limit is actually going to exist, and it's going to be that particular point that we're looking at. So the function is approaching 1 from the left and approaching 1 from the right. Therefore, our limit for number 3 is going to be a 1. Okay, this sort of just kind of get us going in the very beginning. But now check out question number 4. Now they're asking, what is f of -3? Let's look at our graph. What is actually f of -3? Does it exist? Does it exist? It does not. F of -3 does not exist. Why? Because there's a hole there. And that's the difference that you should understand, is that even though the function does not exist, the limit can, because it's approaching something. That's what it means for something to be approaching a value from the right and from the left. So that's why limits are sort of important, because we're observing the behavior of the function as it's approaching a specific value. Yeah, let's go to number 5. So number 5, they're asking for the limit as x approaches -1 from the left side. So same thing, let's go ahead and go to our graph. We're looking at -1, which is here. And now we're approaching it from the left side. Okay, as I'm coming from the left side of the graph, what's the y value that I'm approaching? Well, in this case, it's going to be -2. And let's go ahead and answer problem number 6. What is the function, or what is the limit approaching as it's approaching -1, but from the right side? Okay, let's go back to our graph up there. We're approaching -1 from the right side. So just imagine you're on the graph and you're getting close to -1, and you're asking yourself, okay, what does it approach? It looks like it's 3. Again, technically, it's like 3.00001. It's only approaching it because there's a hole there. But for the sake of, just trying to be as general as possible, we're just going to say that the function is approaching 3. Okay. I left these answers here because for number 7, now they're going to ask us, what is the limit as x approaches -1? Well, remember that I said that the definition of the limit is going to exist if the function is approaching the same value from the left and from the right. In this case, it's approaching -2 from the left, it's approaching 3 from the right. Therefore, a limit does not exist. Okay, keep that in mind. Again, the function is not going to exist because the limit is different from the left and from the right. And now, let me erase these things. So the limit doesn't exist. But number 8, they're asking us for f of -1. So let's go ahead and go to our graph, and they're asking for the y value when x is equal to -1. So it's one of these points. It's either going to be the hole or the open circle. And obviously it's going to be the hole. I said the hole, but it's going to be the closed circle. because you have two options. Again, you have the whole, but you have the closed circle. So it has to be the closed circle because it's defined there. So the answer is -2. So look at what we've seen so far. We've seen a function in problems 1 through 4 where the function did not exist at that specific point, but the limit did. And now for problems 5 and 7, we had a problem where the function did exist at a specific point, but not the limit. So that happens sometimes. So that just goes to show the differences between limits and what the actual function is. Okay. So now let's go to number 9. Number 9, limit as x approaches 2 from the left side. Okay, let's go ahead and go to our graph. This is -2, that's what I'm looking at. And I am approaching it from the left side. So again, imagine I'm on the left side of x is equal to 2, and I'm approaching the function. What am I approaching? Again, technically it's like 2.00001. It's not the actual value, but for the sake of being general here or generalizing our answer, we're gonna say that it is gonna be around 2. And now let's try number 10. Number 10, the limit as x approaches 2 from the right side. Okay, back to our function. You're approaching 2 from the right side. So you're coming from the right side, and we could almost safely say here that it is going to be 1 because there's an actual closed circle. Okay, but what is it approaching? It's getting really, 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 really close to 1. So if you were to zoom this, it's one of those things where like you're just trying to see what is it approaching. So think of it like you have a magnifying glass and you're trying to see what the function is approaching. So if you are on a minuscule level, you will see that it's really, really, really close to 1. But of course, we can say that it is just 1. Whoops. That's what happens when I keep using my highlighter and switching back to my pen. That was number 9. And then, of course, number 11. I haven't seen the problem, but let's write it out. Yes, of course. Now they're going to ask, well, what is the actual limit as x approaches 2 of f of x? Well, remember, the limit from the left and the limit from the right are two different things. Therefore, for number 11, the limit does not exist. And in number 12, I kind of like how they are spacing these out. F of 2 is going to be the function where it's defined at 2. So going back to our graph, it's either going to be the whole or the closed circle. And of course, that will be the closed circle. So f of 2 is going to equal to 1. Awesome. Okay. Let's try number 13. Limit as x approaches 4 from the left side. Okay. So we're obviously observing the behavior of the function when x is equal to 4. So in the graph, I kind of put an arrow there. And again, now we're trying to see what is the function approaching when x is equal to 4 on the left side. Let's see, I'm getting really, really close. What's the y value there? Looks like it's going to be -1. 14, the limit as x approaches 4 from the right side. Okay, same thing. Let's go to our graph, and I'm approaching it from the right side. Yeah, looks like I'm getting really, really close to -1. So this is good. Okay, 15. Now they're going to ask me, well, if you found the limit from the left, limit from the right, what is the actual limit? Ah, this is nice because check that out. The limit from the left and the limit from the right are both the same value. So we can say that this is going to be 1. Awesome. Okay, so now we know the limit from the left, limit from the right was the same thing. The limit actually exists. Problem 16 is they're asking, well, what is f of 4? Well, going to our graph, it looks like there's a closed circle when x is equal to 4. Let me erase the highlighted part. You're just going to see it back on our graph. You're going to see that coordinate when x is equal to 4 is going to be -1. Wow. By the way, for 15, I put 1, but it should be -1. So let me change that now. So number 16 was -1 as well. This is a nice problem. And again, just looking at the graph, there was no holes, there was no jumps whatsoever at 4. So of course, the limit is going to be the same value all around. The limit is going to exist. The function is going to exist at -1. That's what we like to call continuous. So technically, it is continuous at x is equal to 4. Why? Because again, the function was defined, the limit exists, and they're all the same value all around. So that's something that's really, really nice when it comes to continuity. Okay, let's do 17. So the limit as x approaches 6 from the left side. Okay, let's go back to our graph. The limit as x approaches 6. This is 6. Okay, now I'm looking at what it approaches from the left side. And again, it's technically approaching 0.9999999. That looks like that will be the exact value. Again, we will say 0.9999999. That's what it's getting really, really close to. However, just for the sake of generalizing things, we're just going to say that this is equal to 1. Okay? No harm here. They're just asking one simple question. I keep reminding you here because I think there's going to be some problems where we're going to have to think of this 0.99999 value. Okay, so now we have x is equal to, the limit as x approaches 6, but from the right side. All right, let's go back up to our graph. We're approaching 6 from the right side, so I kind of highlighted that there. And in this case, it's not 0.99999, it's like 1.000000001. Whoops, I'm using the highlighted part. There we go, 1.0000001. But of course, we're just going to say that it's going to be above 1. We're going to generalize it. Awesome. Okay, 19. So if we found the limit from the left, the limit from the right, well, what is the actual limit? They're both the same value, so we're going to say that the answer is going to be 1. And of course, hopefully by now you can see the pattern here. Now they're going to ask, what is f of 6? So let's look at our graph, because be very careful. At 6, we technically have a hole where that limit existed. But on top, I'm going to circle this, or I'll highlight it. We have a closed circle. So that's actually where the function is defined at 6. So back to our problem number 20, our function is going to equal to, looks like 3. So there's a big difference. The limit exists, but the function is going to be defined at something else. And right away from the graph, you can tell that there is a removable discontinuity. There's a hole there. So the function is not continuous at 6. Again, in order for something to be continuous, is the limit has to be the same value, the function has to be defined at that specific value. That's mathematically how the limit exists, and graphically you can just tell why it's not going to be continuous. So the function will be continuous if everything is the same value all around, and graphically it is continuous if you have the hole being the actual point where it is defined as well. Awesome, guys. Okay, go to the next slide. Actually, no, 21 lists all the values of x at which the function is discontinuous. Okay, so we've been talking about those things. So 21 is asking where it's discontinuous. So let's go back to our graph. Our graph here at -3. Remember, the limit existed, but the function was not defined. So we say that's 1. So at x is equal to 3, it's discontinuous. At x is equal to 1, the function existed because it was at -2, but the limits did not exist. Therefore, that's discontinuous. So x is equal to -1 is another value. At 2, it was also discontinuous. The limits were different values, but the function existed. So that's 3 points so far. And then the last one that we have was at 6. Why? Because the limit existed, the function was continuous, or the function was defined, but there were different values. So therefore, that's another point of discontinuity. So point of discontinuity was x is equal to -3, -1, 2, and 6. Voila. Awesome. All right, guys, let's go to the next slide. I think I have 5 slides altogether. So hopefully we're getting the sense of these things. Okay. Let's go to part A in this case. So part A is asking what f of 0 is going to be. Okay, all we have to do here is look at our graph and see what the y value is when x is equal to 0. And as you can tell, it is just the origin. So we can say that our answer here is just 0. Okay, what about number 2? Now they're asking for f of 2. What is the y value when x is equal to 2? Well, if we go to our graph, x is equal to 2, looks like there's going to be a vertical asymptote. So in this case, we say does not exist, undefined. Or I guess we can say, the directions are asking you to write dne if it doesn't exist. So we're just going to say dne. And f of 3, what is the y value when x is equal to 3? Well, it looks like it's going to be this point that I highlighted on the graph. It's just going to be 0. Okay, here, very simple questions. They're just asking for what is the y value when the x is equal to, something specific. So they're kind of just warming us up here. And now let's talk about part D. Let me go ahead and erase my work on the graph here. Okay, so now they want part D. They say, okay, the limit as x approaches -1. So let's go to -1 on the graph. Okay, so remember, from the previous problems, we were doing the limit from the left and the limit from the right in order to find the limit. So that's exactly what we're going to do. Let's talk about the left side. If you were continuing on this graph, if you would just imagine yourself on the actual graph and you're riding this wave, and you're coming from the left side, what are you approaching? Looks like you're going all the way upward. So the limit is going to be infinity for that section. Okay, so the limit from the left is going to be infinity. But now let's imagine that you're coming from the right side. So you're riding this cool wave, you're coming down, you're approaching, or you're riding the graph again, and you're approaching -1. Whoa, what happens here? Looks like you're going all the way to negative infinity. So the limit from the left is positive infinity. The limit from the right is negative infinity. Therefore, the limit cannot exist because remember, it has to be the same value. So we're going to, for part D, we are going to say does not exist. Okay. I always like to draw those little stick figures because it's kind of nice. Hopefully it's a good way to visualize it. You're riding this graph and you're trying to see what it's approaching. So think of it like you're on a road and you're trying to see where you're headed. That's really what it is. So you're trying to see what you're approaching. Okay, so part E, the limit as x approaches 0. Okay, well, let's do the stick figure again. You're on this graph on the left side and you're riding this. You're on this road and you're trying to see what am I approaching when x is equal to 0? Boom, it looks like I'm approaching 0. So the limit as x approaches 0 from the left side is going to be 0. And now let's try it again for the right side. You're on this graph, you're riding this wave. And again, what is the limit as x approaches 0 from the right side? It looks like it is also 0. The limit from the left and the limit from the right exists. Therefore, the limit is going to exist at 0. So for part E, we say that the limit is going to be 0. All right, 2 more problems on this slide. Let's go ahead and do part F. Now the limit as x approaches 2 from the right side. From the right side. Okay, so again, I am on the right side of 2. I'm riding this graph. I'm approaching 2 and whoop, it takes me all the way down. That's technically negative infinity. So they're asking for the one-sided limit. This is just going to be negative infinity. Okay, let's go ahead and try part G. Ooh, this is interesting, or it's different. We have not done this. What happens as x approaches infinity? So whenever you see this type of limit, what happens as x approaches infinity? There's many ways of visualizing this. They're really asking for what is a horizontal asymptote. But if you want to imagine it again, just on the graph, you're asking what happens as I continue moving further from the right. Okay, what happens is as my function continues all the way to the right, because this is the limit as it approaches infinity. Well, again, just imagine I'm riding this wave. What happens as I approach, as I continue further to the right? Okay, some people will argue that, oh, it looks like you're going all the way to infinity. But that would mean that I'm going all the way up. And that's not the case, because I have this like wall, if you will. I have a boundary that's not letting me pass. And that is that asymptote. So this function is actually never going to touch the asymptote. The asymptote does not allow us to cross. So for part G, when they're asking me what happens as x approaches infinity, was what happens as I continue moving to the right, my answer is actually going to be 1. It's going to be that horizontal asymptote, because again, I'm approaching it. That's the y value that I'm getting really, really close to. I think that's a best or a good way to represent horizontal asymptote. It's a good way to explain limits at infinity, and hopefully that helps. Again, but if you have any questions, I mean, you're more than welcome to drop some comments in this video. Let me know what else you'd like for me to review. And if you have questions, feel free to message them to me at theveganmathguy.com. All right, guys, let's go to the next slide. Again, today is just all about limits and solving them graphically. So here we go with slide number 3. So it looks like it's the very same type of questions as slide number 2. So here we're trying to find the value when x is equal to 0. So for part A, all they want is f of 0. Well, let's look at that graph. Do we see a y value when x is equal to 0? Some people will argue that it's here where I just highlighted that point. Some people will say, okay, it's 2 and be done. That's incorrect. I wonder why. There's a hole. Okay, so the function is not going to exist at that specific point. It's just a hole. It's not defined there. So in this case, there's actually no y value that the x value corresponds to when it comes to the graph. There is a hole there, so there's no y value whatsoever. Okay, part B, f of 2. Well, that's kind of nice. F of 2, if you look at this, what is the y value when x is equal to 2? It's that point there that I've highlighted. So the answer is going to be 0. Now, a lot of people might say, I mean, at this point, you're in calculus, so this will be sort of a silly question, but it's okay to ask it. There's no closed circle there. So why would it be 0? Well, technically there is. We just don't draw it. Okay, so keep that in mind. Unless there's a hole, we're going to assume that it is going to be a closed circle. So for part B, f of 2 is equal to 0. And now we go to f of 3. F of 3 is going to be interesting. So you have 3 choices. You have 1, you have 2, or you have 3. Well, remember, the first 2 are just holes. So they're not defined, they're holes. So the only value where it is defined is that closed circle. So our answer for C, f of 3 is going to be 3. All right, now we're getting into some limits. They love to introduce, like, what is the function? What is the limit? I think knowing the differences between those is important. All right, so now we go to the limit as x approaches 0 from the left side. Okay, so just imagine I'm on the left side of 0. I am on top of this graph, and I'm going to ride this wave, if you will. I'm going to ride this function. And what happens? Whoop, I get sent all the way downward. So my limit as x approaches 0 from the left side is going to be negative infinity. I'll write that down. That's a terrible infinity. Let me erase that. That's better. Okay. So now let's talk about part E as x approaches 0. Just 0. This is interesting. So they kind of just jumped the gun there. So we did the limit as x approaches 0 from the left side. It was negative infinity. Just to, show what the limit is actually going to be, let's also figure out what the limit as x approaches 0 from the right side is going to be. Hopefully you can kind of tell already. But again, let's go ahead and go to the right of 0. This is where I am. I am writing this graph and I am approaching 0. And again, my answer is not the answer is not actually 2. I'm approaching 1.9999999, something really, really close. But for the sake of generalizing this stuff, we say that it is going to be 2. So our limit is going to be 2 as it approaches 0 from the right side. So back to part E, what is the actual limit? Well, keep in mind the limit from the left is negative infinity. The limit from the right is 2. So the limit is not going to exist. And you can almost tell that's going to be the case here, obviously, because we have a jump. Here's a bonus question. I already know doesn't seem like they were asking that. Is it continuous at 2? Or is it continuous at 0? I guess that's my question. Continuous at x is equal to 0. Well, the limit from the left and the limit from the right are two different things already. So it kind of failed that test. Remember, we want it to be everything or the same value all around. We want it to be defined at a specific value. We want the limit from the left and the right to be that specific value. And we want the limit naturally to be that specific value as well. But in this case, they have all these different videos, or they have all these different points that it's approaching. So we're going to say that that is not going to be continuous. Okay, so now the next question, they're asking whether or not the limit is approaching, or what the limit is approaching when x approaches 3 from the right side. So part F. So let's go ahead and write this function again. The limit, I'm on the right side of 3, and I'm getting really, really close. Once again, this answer is like 1.9999999, but for the sake of generalizing this, we're going to say that the limit is going to be 2. Okay, for part G, again, it looks like they just jumped right ahead and asked us about the limit. Hopefully you can already tell this is not going to exist, but we're going to see why. So first, let's just do the limit as x approaches 3 from the left side. Okay, I am on the left side of the graph. This is my little stick figure. I am coming down on the left side. What am I approaching? Technically, it's like 0.9999999, right? It's getting really, really close. But for generalizing it, we're going to say that this is going to approach 1. So the limit from the left is 1. The limit from the right, which we found in part F, was 2. So therefore, in part G, does the limit exist? No, it does not, because the limit from the left and the limit from the right are two different values. So we're going to say D and E. Okay, let's go to part H. Hope I erased everything, but that's okay. Ooh, so for part H, another thing where they want us to observe these values, or they want us to observe the end behavior. So for part H, the limit as x approaches negative infinity from, or just approaching negative infinity, not even from the left side, from the right side. So the limit as x approaches negative infinity. So again, just imagine you're on this graph and you're going all the way to the left. So you're kind of like ending up here already. And then again, you're just trying to observe what happens as I continue moving to the left. Well, keep in mind, there's that asymptote. It's not really drawn as nicely as you want it to be, but you kind of have those dotted lines there. So the dotted lines, again, what they do is they create a little boundary and saying, hey, you cannot cross. You shall not cross on the left side. So as I'm approaching negative infinity, as I'm moving all the way to the left, then the function is being bounded. So the function is not allowing me, or the intercept, the asymptote is not allowing me to cross there. So what is it approaching? It's close to 1. So it's like 0.9999999, but it's so close that we're not even going to write we're not going to write that. We're going to generalize it and say that it is going to approach 1. Okay. This is good. Let's go to slide number 4. This is I like this one, and I'm hoping that we see, whoops. Okay, here we are. I'm hoping that we hit a little snag. This is usually what we see in Calc BC. I had a student where we were doing some limits, and we kept getting does not exist in a lot of the problems. So I'm hoping this is one of those situations, and you'll see what I'm talking about if that actually happens. So let's talk about part A. So for part A, they want this limit, but check that out. Now we have two different functions. So something that we have to learn is when you have two limits like this, you can actually separate this and take the limit of them separately. Okay, so whenever you have the sum or difference of two limits, you can just go ahead and take the limit of them separately, solve them individually, and see what the value is going to be. Okay, so let's just first talk about the limit as x approaches 2 for f of x. Okay, the limit as x approaches 2 for f of x. Well, again, looking at our function, just because, we've been doing so many limits from the right and the left, that's exactly what we're going to do. We're just going to draw that real quick. We're just going to visualize it on the graph. So let's see, if I'm on the left side, it looks like I am approaching, it's like 1.9999998. It goes on forever, but we're just going to say, to generalize it, the limit as x approaches 2 from the left is going to be 2. What about the limit as x approaches 2 from the right? Well, let's see again. I am on the right side of the graph and I am approaching 2, and it looks like it's still the same thing. It's going to approach 2. So therefore, back to our problem, the limit as x approaches 2 of f of x is just going to be 2. So we're going to write 2, and then we're going to have plus. And now we're going to go ahead and try to solve the second limit, the limit as x approaches 2 for g of x. Okay, so let's go ahead and do the limit as x approaches 2 from the left and the limit as x approaches 2 from the right. So from the left side, it looks like I am approaching 0. And then from the right side, same thing. It looks like I'm also approaching 0 there. So back to our problem, the limit is 2 plus 0. Therefore, our limit is just going to be 2. Okay, hopefully you were able to see that. Okay, let's go to part B. Hopefully we can see that and understand that. Okay, so the same thing for part B. I'm just going to separate it. So I'm going to do the limit as f of x as x approaches 1 plus the limit of g of x as x approaches 1. Okay. This is really, really interesting. Okay. So let's talk about the first one. Okay. Limit as x approaches 1. If I try to do, again, the one-sided limits, what we would get, it doesn't look like we have to really observe too much. I mean, it's just crossing both points, the same value from the left and the right. So we're just going to say that that limit is going to equal to 1. So we know that the first limit of f of x is equal to 1 plus, and then let's talk about this next one, the limit as g of x approaches 1. Okay, so it looks like we might have to just observe the limit as x approaches 1 from the left side, and then the limit as x approaches 1 from the right side. Okay, let's look at our function. The limit as x approaches 1 from the left side. That's coming here. And it looks like it's approaching 2. But the limit as x approaches 1 from the right side looks like it's approaching 1. So the limit doesn't exist because the limit from the left and the limit from the right are 2 different values. So that's dne. So what happens here? We have 1 plus dne doesn't work for us. So we're going to say that this limit, the sum of the limit of f and the limit of g, does not exist. Okay, hopefully that made sense for you guys. Now let's go on to problem C. So now we have the limit as x approaches 0. All right, the limit as x approaches 0. So again, we have this product of limits. And when you have this, what you can do is you can also take the limit of them individually and just multiply them out. Okay, let me try a different method here. I'm going to continue doing this, but I'm going to do 2 things. I'm going to do the limit as x approaches 2 from the left. Let me just write that in different colors. Okay, the limit as x approaches 0 from the left times the limit as x approaches 0 from the left. That's going to be one limit. And another limit, hopefully it fits, the limit as x approaches 0 from the left times the limit as x approaches 0. Oh, I said from the left, but I meant from the right. The limit as x approaches 0 from the right, and then the limit as x approaches 0 from the right for g of x. Hopefully that you can understand what I wrote there. I know that the writing is kind of bleeding onto the work there, but hopefully, you can see that. Okay, so let's just talk about the limit as x approaches 0 from the left. So for my first graph for f, as I approach 0 from the left, it looks like it's 0. Okay, great. And then let's go ahead and look at it from for g of x. As x approaches 0 from the left, gosh, it's like 1.5. So then our limit, back to our problem, is 0 times 1.5, which of course is just going to be 0. Okay, so now let's do the right side. For f of x, As x approaches 0 from the right side, it looks like it's going to be 0 times, and then let's go to our other function. As x approaches 0 from the right side, it actually looks like it's also equal to 1.5. Okay, cool. So again, here I'm just, if you want it to be more specific, so 0 times 1.5 is 0. So what is our limit? The limit as x approaches 0 of the product of these functions is going to be 0. All right, cool. So it's important to, especially if you're feeling confused, it's never a bad thing to observe limits from the left and from the right. Continue doing that if you need to. I think that's always a good method to do, especially when you have these types of functions, f plus g. There's other scenarios where this is really, really helpful. And that's especially happening when you have like f composite g here. I'll write this down in red. So when you have like f composite g or f composite f, that's always interesting. That's always important to visualize from the left and from the right. But again, let's go ahead and go to part D. So two limits that I'm going to do. I'm going to do the limit as x approaches -1 from the left of f of x over the limit as x approaches -1 from the left of g of x. And we're also going to look at limits as x approaches -1 from the right of g of x over the limit as x approaches -1 from the left of g of x. Okay, so let's talk about the back to the problem that at the very end it should be -1 to the right. When you're saying or when you're writing these things down, God, it takes you're thinking of so many things, especially as you're saying limit from the of f of x as x approaches -1 from the left. I mean, there's so much wording there that sometimes you get confused. So let's go back to the limit as x approaches -1 from the left. So our function, if we're looking to the left of -1, looks like it approaches -1. Okay, so back to our problem, I have -1 divided by, and now let's go observe what happens as x approaches -1 from the left, or g of x. Ooh, it's 0. Oh my goodness. Okay, -1 over 0. That is okay to have. It's not like it's indeterminate. It's okay to have. Right now, we're going to say that's undefined, but we're going to leave it like that for now. First, let's just go ahead and check what the limit from the right is. So for f of x, as x approaches -1 from the right, it looks like it's also -1. So I'm going to go ahead and put a -1 next to it on my limit. Hopefully it fits. -1. Yes, looks like it does. And let's go ahead and see what g of x approaches when x approaches -1 from the right. And what do you know? 0 as well. Ooh, I love having this. So -1 over 0, obviously, is not an ideal answer, but that still tells us something about the limit. So the limit does not exist at that point. It is going to be undefined. It's both -1 over 0. That doesn't mean that it's indeterminate. That's something that we're gonna see in calculus, hopefully within the next few lessons. But right now, we're gonna say that this is undefined. The limit from the left and the limit from the right both give us an undefined answer, so we're just gonna say that the limit is undefined. This is interesting. I like that one. Okay, so let's go ahead and try E. So part E, here we're just looking at the limit as x approaches 2 from, just the limit as x approaches 2. Now, here's the thing, okay? I think a lot of people are already just going to jump the gun and say, okay, well, if I'm doing this, can I just, let me erase this. If I'm doing this, can I just do 2 cubed times f of 2? You absolutely can, okay? And I think you can do that. It's what we call direct substitution. But the one thing that I will be very careful with is just keep in mind that this is the limit. So we're trying to see what it approaches. So what we're going to do is, again, we're going to check the limit as x approaches 2 from the left side of x cubed f of x. And then what happens to the limit as x approaches 2 from the right side of x cubed. f of x. Okay. So what happens is we approach 2 from the left side. Well, for the first value, that x cubed, think of it, if you're coming from the left side, a number that's to the left of 2, but really, really close to 2, it's like 1.9 or 1.99. Guys, hold on. I think I'm about... Oh, okay. Just making sure I'm playing music in the background and I don't want there to be ads and then get a copyright claim from YouTube. So I kind of panicked there. Okay. So back to this problem, we said, okay, well, what is a value that's to the left of 2 but approaching it? It's like 1.99. So really what we're doing here is we're plugging in 1.99 cubed times, and then now we're trying to see what the limit as x approaches 2 from the left is for this function. So looking at the graph, 2 from the left, it is also about 1.999. Okay, so right now our limit is 1.99 cubed times 1.99. Okay. So this is about, again, if you were to estimate this, because it's about 2. So really this is like 2 cubed times 2. So then we can say that this is going to be 16. Okay. Well, let's look at the bottom value now. So a number that's approaching 2 from the right side, that's like 2.001. So we're really trying to find 2.001 cubed times the limit as x approaches 2 from the right side. Okay. Well, looking at our graph again, if we approach 2 from the right side, that's about what? Again, 1.999. So we have 2.001 cubed times 1.99. And again, it looks like that's about the same value. It's about 16. Okay, so then the limit from the left and the limit from the right is approaching the same value. Therefore, for part E, there on the bottom, we can say that our limit is going to be 16. All right, we're going to utilize that same energy for part F. Okay, so we're going to do 2 things. Almost done. We got perfect. Okay. All right, so if I'm taking the limit as x approaches 1, I'm going to do the left side first. This is going to be square root of 3 plus f of x. And then I'm going to look and observe the limit as x approaches 1 from the right side of 3 plus f of x. Okay, luckily for us, that 3 doesn't matter. It's just a 3. So let's go ahead and look at the value as x approaches 1 from the right side. So back to our function or our graph. As x approaches 1 from the left side, it looks like it's like 0.0.99999. Okay, we're just asking what it's approaching. So back to our limit, we're just going to write root 3 plus 0.999. And if you were to actually think about it, 3 plus 0.99999 is like 3.99999, obviously, which approaches 4. So we can say that this is going to be the square root of 4. So it's just going to be 2. We're going to use that same idea for the other limit. So the limit as x approaches 1 from the right. So if I'm on the right side, it looks like it's not 0.999, it's 1.0001. Okay, so now we have the square root of 3 plus 1.0001. And again, that's like the square root of 4.0001, which is very close to 2. Okay, but this is why it's important, because we're looking at limits as they approach something, not what the actual value is. Okay. Give me 1 second, guys. Okay. Oh my gosh. I gotta find some better audio to play because it just continues to skip back and forth. All right, guys. Anyway, back to this. We're almost done. We have one more slide to do. Hopefully this makes sense for all of you so far. This is all about just limits, baby. Today we were just messing around with all these limits, trying to understand what happens when you approach values from the left and from the right. Yeah. Now, this particular question is testing continuity at -1, at 1, and at 2. It looks like that's a -1.1, but I promise that it is a comma. Okay, so let's just talk about x is equal to -1. So this is a specific test, and you're going to see that this looks like all the problems that we did in slide 1. So the first test that you always want to check, especially for x is equal to -1, is find out what f of -1 is. Okay, so let's look at our graph. F of -1, we are looking at these 2 points, and we're going to choose the one that has the closed circle. So in this case, it's going to be 0. Okay. And now step 2 is to find the limit as x approaches -1 from the left, and find the limit as x approaches -1 from the right. So technically what that means is we're trying to find what is the actual limit as x approaches -1 of f of x. Okay, well, let's talk about what's going on the left side. As I'm coming from the left side, just again, imagine myself here, and I am writing this graph, and I am approaching, oh, it looks like I'm approaching 1. And now let's go ahead and do the other side. What happens as I approach -1 from the right side? It looks like I'm approaching 0. So back to our problem, I'm going to go ahead and write 0 for there. So remember, the limit from the left, the limit from the right are 2 different values. Therefore, the limit, the actual limit, does not exist. And so the next condition is both problem 1 or condition 1 and condition 2 have to be equal to each other. So we're going to say 1, so like 1 does not equal 2. So condition 1 and condition 2 is not equal to each other. Therefore, f of x is not continuous at x is equal to 1 or -1. Okay, that's important to understand. 1, it's defined. 2, the limit exists. And 3, condition 1 and condition 3 are equal to each other. If you recall, these 4 steps, the function being defined, the limit from the left, the limit from the right, therefore the limit, they all had to be the same in order for the function to be continuous. And that's what we did in slide 1. We said if all these are the same, then we're good. We know it's going to be continuous. Otherwise, it's not going to. All right, let's try x is equal to 1. Remember, condition 1, find f of 1. Well, f of 1 is literally just that point. And remember, we said even though there's no closed circle, there's no hole whatsoever. So we know that it's going to exist there. So it's going to be 0. 2, the limit from the, as x approaches 0 from the left. Whoops, as x approaches 1, I'm sorry. The limit as x approaches 1 from the right. And then the limit as x approaches 1 at the end is what we're going to try to find. Okay, so from the left side, again, if I continue writing that graph, it looks like I'm approaching 0. From the right side, it also looks like we're approaching 0. This is great. Both of these values are the same. Therefore, the limit that we have at the end is going to exist, and it's actually going to be 0. Look at that. All 3 conditions are equal to each other. Boom, boom, boom. That's what we want. This is perfect. So then for step 3, we say condition 1 is equal to condition 2. And therefore, that's what those 3 little dots mean. F of x is continuous. And I'm going to put at x is equal to 2. Awesome. Okay, cool. And so now let's do this last one at x is equal to 2. We have f, so remember we said, whoops. I hate that I'm doing different colors. So 1, f of 2. Okay, let's look at the function. Be very careful here. We have a hole, but then we have a function defined up there, up on top. So we know that we're going to have to use the closed circle. So we know that this is going to be 2. Okay, step 2, the limit as x approaches 2 from the left, the limit as x approaches 2 from the right, and now we have the limit as x approaches 2. Okay, from the left side, looks like it's approaching -1. This is a weird diagram, but yes, it's going to be -1. Okay, the function as it approaches 2 from the right side. Also -1. Okay, that's nice. So then naturally, because the limit from the left and the limit from the right are both going to be the same value, we are going to say that this is going to be -1. The limit actually exists. But again, the three conditions work here: the limit from the left, limit from the right, and then the actual limit. But then it does not equal the top function or the top condition. So again, for step 3, let me just erase this in blue. So for step 3, step 1 does not equal to step 2. Therefore, f of x is not continuous at x is equal to 2. This is exactly what you have to do. So if you're taking calculus and if they're asking you whether or not a function is defined, and usually they're going to say, go ahead and test it. This is what you're going to have to do. Okay. All right, guys. So far, that is all I have right now. I hope that you've enjoyed this. I'm hoping that that you're liking this material so far. But again, I'm gonna continue going live every day, every weekday at least, covering whatever sections you guys have or whatever sections or problems you might have. But if I find something that I think that a lot of people are gonna have interest in, that's exactly what I'm gonna review. But of course, if you have any questions, you can always go to my website, theveganmathguy.com, and post your homework. And that's it. I think that's it for today. How long did I go for? I don't know how long this is going for. Yeah, I don't know. I don't know how long I've been going for, but this has been fun. Yep. All right, guys, don't forget to like this video, comment what you want me to review, follow me on Instagram, follow me on TikTok. And until then, happy trails.